All right, let's dive in. Today, we're basically becoming mathematical detectives. We're going to crack the code on a type of differential equation that looks kind of tough on the surface, but once you see the clues, it has this really elegant, logical solution. So, let's open up the case file on exact differential equations.
So picture this. You walk up to a crime scene and it's a complicated differential equation. It looks like a total mess. Maybe a little intimidating, right? But what if I told you that all of that apparent chaos
Was really just the set of footprints left behind by a much simpler, cleaner parent function. We'll call it f of x comma y. And that's the whole game with exact differential equations. We're basically detectives on the hunt for that original, hidden function.
Okay, so let's get into our case file. The kind of equation we're looking at today, our person of interest, if you will, is any first-order differential equation that you can write in a very specific way.
It's always going to look like this. Some function m, which has x's and y's, times dx, plus another function n, also with x's and y's, times dy, all equals 0. Our whole mission here is to figure out if this entire expression is actually the total differential df of that secret function f we're looking for. Because if it is, then df equals 0, and solving it becomes way easier.
So this leads us right to our prime suspect. What does it even mean for an equation to be exact? Let's get a formal definition down so we know what we're looking for. So, exact isn't just a random word here. It means that the mdx plus ndy part isn't just a jumble of terms. No, it's the complete and perfect derivative of some other function. Think of it like a perfect set of breadcrumbs that leads you right back to the source.
And this is the connection that just makes everything click. Now, you might remember from multivariable calculus that the total differential of a function f, or df, is the partial derivative with respect to x times dx, plus the partial derivative with respect to y times dy. So if our equation is exact, that means m has to be the partial with respect to x, and n has to be the partial with respect to y. They're two halves of the same whole.
Okay, so that's all great in theory, right? But how do we actually prove it? I mean, how can we be sure an equation is exact if we don't even know what the secret function f is yet? Well, luckily for us, there's one incredibly simple, super powerful test we can run.
This is our forensic evidence. This is the one clue that tells us if we've got a solid case or if we've just hit a dead end. Seriously, this little test is the key that unlocks the entire method.
And here it is. The whole thing comes down to this one idea. You take m and find its partial derivative, but with respect to y. Then you take n and find its partial derivative, but with respect to x. If those two things are exactly the same, the equation is exact. It's that simple. So, this is it. This is our fingerprint analysis. Now, you might be wondering, why does this work? It's actually because of a really neat result from calculus called Clairaut's theorem, which basically says that for most functions we care about, the order you take partial derivatives in doesn't matter. So if they match, it's exact. If they don't, it's not. It's a clear yes or no. And seeing it in action just makes it crystal clear. Look at the left side. The partial of m with respect to y is 2x. The partial of n with respect to x is also 2x. Boom! They match. It's exact. Now look at the right. The partials don't match up. The test fails. That equation is not exact. See? A clear pass or fail every time.
All right, so our test came back positive. We've confirmed our equation is exact. Now we move into the interrogation room. We know there's a hidden function, f of xy, hiding in there, and we're about to follow a step-by-step procedure to get it to talk.
This is our 5-step game plan. We're basically going to work backward. We start by integrating m to get a big piece of our function. The key move here is that our constant of integration is actually a whole function of y, which we call g of y. Then we use n to figure out exactly what that missing g of y piece is. It's a really methodical process for revealing that hidden function.
Okay, enough theory. Let's get our hands dirty and actually put this procedure into practice. We're going to take one case from the initial test all the way to the final reveal. Let's do this.
Here's our suspect, 2xy dx plus the quantity x squared minus 1 times dy equals 0. Yep, looks like it fits the mdx plus ndy profile perfectly. First things first, always run the test. M is 2xy, n is x squared minus 1.
Okay, partial of m with respect to y is 2x. Partial of n with respect to x is also 2x. We've got a match. The equation is confirmed to be exact. We have a green light to proceed. Now for the interrogation. We start from what we know. The partial of f with respect to x has to be m, which is 2xy. So we integrate 2xy with respect to x. That gives us x squared y. But, and this is the crucial part, we have to add our constant of integration, which in this world could be any function that only has y's in it. So we add g of y. Okay, next move. We take that function we just built and differentiate it, but this time with respect to y. The derivative of x squared y is just x squared, and the derivative of g of y is just g prime of y. Now for the magic. We know this whole thing has to equal n, which is x squared minus 1. So we set them equal, and look at that. The x squared terms on both sides just cancel out, leaving us with something incredibly simple. G prime of y equals -1. We are so close now we're on the home stretch. We just need to find g of y, and we know its derivative is -1. Well, what function has a derivative of -1? We just integrate it with respect to y, and that gives us -y. That's it. We found the last missing piece of the puzzle.
And now for the final reveal. We take our g of y, which is -y, and we plug it back into our expression for f. That gives us our hidden function. F of x comma y is x squared y minus y. And because the original equation was df equals 0, the general solution is just our function f, set equal to a constant, c. The hidden function has been found. Case closed.
So, we've figured out how to spot an exact equation and how to solve it. But what about all those other cases? The ones where the test fails, where our fingerprints just don't match? Is it a lost cause? Or is there a way to, let's say, persuade a non-exact equation to become exact? Well, that's a whole other mystery for another time.